Excuse me. Hey, everyone. Let's go ahead and take a look at how to analyze this series circuit, knowing some particular values now that we've drawn it. So this is right. This is the same as it's a battery in question number 2, right? That has the particular values down below. So I have my drawing that I put in, but now I've got this voltage of the battery. I've got my 3 different resistors, and I can go ahead and figure some things out. Part A asks me to find the total resistance, right? So this total resistance right here. This is a series circuit, so I can go ahead and say that my total resistance, right, is equal to the 3 different resistors just added up straight. Wow, can't even draw R. All right. That should be a 3. All right, there it comes into. So here's my 3 different resistors, and my values are right up here at the top, so I can just put those in, and I can follow along and say that this is 280 ohms plus 110 ohms plus 50 ohms, right? So that's 280. Doesn't look like a 280. 280. There we go. 280 ohms, 110 ohms plus 50 ohms. And so I just add those out straight. 280 plus 110 is 390, plus 50 gives me 440, right? So here's 440 ohms, and this is my total resistance. So RT, total resistance. So number 1 is, or A, I guess I should say, A is done here with my total resistance being 440 ohms. Now this is going to come in handy when we're finding things like the overall current. Remember that the overall current, we can use this Ohm's law, this V equals IR. I could then solve V equals IR for I, which is the current that I want, and I is equal to V over R. I could use my magic triangle to do so, or I could just use algebra to figure this out. But in the end, this is my relationship. My current is equal to my voltage divided by resistance. So for part B, right, my current is equal to my voltage divided by my resistance. And this is going to be my total voltage. That's specifically the battery voltage there that I'm looking at. Divided by my resistance here, which is the resistance that is total as well. And so I can plug those 2 things in, no problem. And it says that my voltage is given here as 12 volts. So I've got 12 volts from the battery. I've got my total resistance of 440 ohms. And if I put those 2 things out, that'll give me my total current as a whole. So this is not something that I've memorized, so I'm going to have to go ahead and plug it in. So I've got 12 divided by 440, and I'm going to come out with a pretty small number of 0.027, and the units on this one are amperes. Now, in all honesty, these small units of amperes, small numbers of amperes are pretty common, which means that it is extremely normal for us to write things in milliamps as opposed to writing things into amps. And you might have run into that if you thought about milliamp hours for cell phone batteries and bits like that. So this being the case, we sometimes rewrite this in milliamps. And if we write it in milliamps, we're going to move our decimal point 3 to the right, which is kind of an or. This is 27 milliamps. So that's a common thing to do, is to have things given in milliamps. There you go. All right, part 3, or part C, I should say, is the current through each resistor. Okay, so if we're looking at the current through each resistor, we know that we have 0.027 amperes as your overall current. And if it's a series circuit, it means that the current flows the same through every component. It does not flow faster through one place versus through another place. So I would say on part C, it is the same everywhere. That's everywhere. Let's try everywhere. Every. Good, everywhere. Ha! can't write today. And the answer to that is 0.027 amps, right? Or you could say it's 27 milliamps. But either way around, this is what we've got. All right, so for our last piece, we've got the voltage drop across each resistor. And the voltage drop across each resistor, let me choose a color. Maybe I'll work in purple. I don't work in purple very often. Means that I can once again use my V equals IR to be able to figure this out, recognizing that I've got three different resistors. So on part D, we've got V equals IR, where V in this case would be V1 is equal to the current through it times my resistance, but my resistance is going to be my R1. And I can just multiply these these two things together, and I'm going to get a final answer to it as a whole. So let me move this over a little bit so we've got a little bit more space to work. So my current is 0.027 amperes. And I'm going to multiply that times my resistance, which is 280 ohms. And therefore my voltage, right, I'm going to use my handy dandy calculator again, is 0.027 times 280. And I walk away with 7.56 volts. So for this first voltage over here for V1, it's 7.56 volts across there. V2 is the same idea here with the common current and now a new resistance, right? Where the common current is 0.027 amperes. And I'm going to multiply that times my second resistance, which is 110 over here. So I've got 110 ohms. And I'll multiply those two things together. So I've got 0.027 times 110. And I walk away with, let's see if we can put it in here, 2.97 volts. Good. My third third voltage, same deal that we did before. I've got my current now times my third resistor here. Same common current, 0.027 amperes. And I'm multiplying this times my last resistor, which is 50 ohms. And we'll go ahead and do that here, times 50. And I get 1.35 volts. Now, I'd like you to take note, right, that my voltage is the greatest here when my resistance is the greatest. And think about this in terms of pressure differences between one side to the other. If there's flowing charge that's coming over here and it gets to a large resistor, there is a buildup of pressure on one side and a release of pressure on the other side, and which means that the voltage, right, this change in energy from one side to the other, or electrical pressure, would be the largest amount. The other thing to note is that if we did this correctly, these three different voltages combined, if I was to take 7.56 volts and then add that to 2.97 volts and then add that to 1.35 volts. So if I was to add these three things up, what do I get? Well, what I should get is the kind of red to blue voltage difference, which is 12 volts. And do I? Well, taking a quick look at my calculator, I get 7.56 plus 2.97, if I've typed that in correctly, plus 1.35. And what I do get from that is 11.88. How in the world did I get 11.88 if it's supposed to sum up to 12? The answer is that all of these values over here are rounded. And so by rounding these three different values, I have lost 0.12 volts in rounding changes. So keep that in mind that when you round numbers, you end up getting slightly different amounts. These three values here should add up to the total voltage. They don't exactly because of rounding differences. All right, ladies and gentlemen, we're going to leave it right there, and that's how you analyze things in a series circuit. Hopefully that was useful, and I'll see you in the next one. All right, take care. Bye-bye.